Okay, well, let's continue. So, want to introduce another discrete random variable called the geometric random variable. We say x is geometric p if x counts the number of independent Bernoulli p trials until a success, that would be the x equal 1 case, occurs. And we can write a PMF for this. So we have p of x then would just be equal to, or you could put k if you like to use those better for positive integers. P of x is then equal to, well, if it counts the number of trials and we're just waiting on a success, then I need the probability that x is equal to little x will be the probability that there were little x minus 1 failures and then finally a success. And there's only one way that can happen. It's have to have fail, 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 success, say. So this is just equal to, I need little x minus 1 failures, and then I get a success. And this is for x equal 1, 2, right? It's got to be at least 1. And this is otherwise. If I put a fraction in, or 0, or a negative number. So sorry, this should be 0 here. 0 x else. Okay, so for example, number of rolls of dice, let x equal number rolls of dice until sum equals 9. Then we would say x is geometric. Probability of a 9 is 1/9, 4 out of 36, so 1/9. Okay. I hope you don't think that's because the sum is 9. All right, yeah, pretty straightforward idea. It's related to the Bernoulli, obviously, and also to the binomial in a sense. You're doing a sequence of independent yes, one or zero, yes or no trials, and you're just counting how long it takes until you get your first success. Well, a superset of this one is the negative binomial. We can say x is negative binomial. And here we will use R and P, and this is the number of rolls. X is the number of independent Bernoulli P trials until, what do you think? Until rth success. So if R is 1, it's geometric P. But in general, you could wait for more than one success. So in this case, P of x is equal to, well, let's see. I need, if I'm going to have R successes, I need P to the R. And then I would need x 1 minus P to the x minus R. But I'm going to need to also adjust a little bit. So I have 1 minus P, x minus R. Those are the fails. And now I have P to the R. But I also have to count how many ways this can happen. And the last trial is constrained to be a success, because that's when you stop. So it's the previous x minus 1 trials that you need to pick R minus 1 successes. So this should be x minus 1, R minus 1. Okay, x minus 1, choose R minus 1, and 0 else. And this starts with x equal R, right? You need at least R trials you get to get R successes, so R plus 1. Okay, so for example, let x equal number rolls until, let's make it 8 comes up 5 times. Okay, well, probability of 8 is 5 over 36. So let's say probability x equals 17. This would just be calculated. I could just use the work I did up here, right? So this is just 16, choose 4. And then I have 1 minus 5 over 36, so that would be 31 over 36. And how many of those do I have? I have 12, and then 5 over 36 to the 5th, right? Okay, whatever that is. I didn't do it. So this is a negative binomial. So one of the reasons to include these words and these descriptive types is that you don't have to go back and redescribe experiments once you've used to the vocabulary. You can just refer to the random variables by their type, and then and then it makes things easier. So you don't have to keep moving forward like every time when setting up an experiment and word problems, and you can just proceed. All right, so the next idea, so those just, I wanted to introduce those two so we had more to work with. So the next idea is the expected value of a function. So expected value of a function of drv x. So I have a drv x and I take a function of it. What's e of g of x? So e well, one way to look at this is if x is a map from, if x maps from S to the reals, right? This is x. And then g maps from, in general, from the reals to the reals, so this is g. Then we just have g of x is really just another map from, it's just another random variable. It's just another map from S, the sample space, to the reals. So we could just treat it as such. Now, I feel, what's the time? Okay, so how do we compute this? So method one, so there's two ways to compute EG of x. So let's do an example. So example, suppose x is equal to sum of two dice. And let g be a function, say g of t is equal to, let's just pick some random funny thing or something, say 100, or else it's 0, just some easy thing. And this is if t is greater than or equal to 10 and else. So I can draw a picture of g here, right? So I have 10. All right, so we want to compute, find E, G, X. Well, there's two distinct ways. One is to actually redefine a new random variable, G of X. So we could let, so method one, let Y equal G of X. Then the PMF of Y is either equal to 100 or 0. So PMF of Y, which usually will put a subscript if you start to get more than one random variable. Could have also said PG of X. So this is equal to two distinct probabilities, and this is if, one would be if Y equals 100, it's one thing, and if Y equals else, right? If Y is 100, the probability is one thing. Y equals 0, it's going to be something else. And then else, it's going to be 0. So these two have positive probabilities. Probability Y is 100 is if I have a 10, an 11, or a 12, that's 1/6. and this is 5/6. So 5/6 of the time y will be 0, and 1/6 it will be 100. So in other words, y really is a Bernoulli 1/6 random variable. It's a funny way to do it, but it's this also. So we could do e(g) of x. So e(g) of x is just equal to e of y, which is just 1/6. Oh, it's not quite Bernoulli, right? Because it's 100 here. So it's 1/6 times 100 plus 0 times the other thing. So it's just 100/6. Okay, so that's e(g) of x. The other way, so 2, proposition, e(g) of x can be done by, instead of weighting x, just weight g of x here. And this should make sense. I'm not going to prove it. There's like a 3-step proof in the book if you want to see this. So this is over all x, p of x greater than 0 if you're fussy. Okay, so if we do it this way, what we get is, so for our example, what do we get? We get a lot of zeros, right? So we have 0 times, because first one 0, plus 0 times 2/36. So this represents rolling the 3. 0 times 3/36, and it continues, plus 0 times, for 9, I have 4/36, plus 100, probability I get a 10. And it should be clear, this comes from exactly where this comes from, and a proof can be done of this by just using symbols instead of actual numbers. So this result gives me the same thing. Okay, we have to stop here. Let's stop here. See if there's one more idea. Yeah, so we'll continue on the next one.